Hello and welcome to What's Inside, the video series on this channel where we do exactly that. We look inside of various, mostly guitar-related devices, effects and all sorts of ancient equipment. Today we're going to look inside of two Watkins copycat tape delays. You could say they're twins, but rather the non-identical variety of twins. They do look similar on the outside and the inside, but there are various differences between the Copycat Super IC and the IC300. The time frame for these two units is the second half of the 1970s, and the amplification inside of both is done by integrated circuits, in short ICs, the namesake for both of them. This video consists of three main sections. In the first two, we are going to see what's inside of the two devices individually. Each section will start with an overview of the main components of the respective device, and then we'll take a closer look into what's the most important facts to know about these components. At last, we will take a closer look into the differences between both copycats and what's their significance. Let's start with the IC300. We will begin with a look at the schematics and break the circuit down into its individual sections first. This approach makes it way easier to find our way around what's what inside the IC300. I found these drawings on the internet and you will find the link in the video description. So it all starts with the input section in the upper left corner. 4 input jacks, 4 gain potentiometers and the first amplification stage, the first IC. The next section consists of the second amplification stage, or in this case the recording amplifier. And of course the recording head, which is drawn right here. Right above the recording head is the erase head, which I'd like to put in the next section, the so-called oscillator circuit. So that was the upper half of the schematics. The fourth section is right here, the playback section. As the name suggests, we here have the three playback heads and the playback amplifier. And here we also have the selector switches for the individual playback heads and a switch for a tone control. And here you can see two additional potentiometers labeled swell and sustain, and a foot switch jack, but we will discuss these parts in much more detail later. The next section is the output stage. And last but not least, the motor, the transformer and everything that has to do with rectification. Let's call it the power stage. Okay, so we have broken down the circuit into 6 logical sections. Let's identify these now on an actual photograph of the insides of the IC300. Well, what you see here is basically the faceplate of the device, and all electronics are mounted on the faceplate. And we have our schematics right at hand, so we can switch back and forth to discuss each section. Alright, let's start again with the input. We have our 4 input jacks, 1, 2, 3, 4, the 4 gain potentiometers, and right here the first amplification IC. Next, the recording amplifier and the recording head. Well, you obviously can't see the recording head in this photograph because it's on the other side of that faceplate, but we can see the wire leading to it right here. And we see the recording amplifier, which is hidden behind that capacitor here. The third stage, the erase head and the oscillator. Again, the erase head is not seeable in this picture, but we see the wire leading to it right here. And the oscillator is a separate board mounted right here. Okay, now the playback stage. We have our 3 connections to the playback heads right here. And we have the 4 selector switches, 1, 2, 3, and the 4th is the tone switch. We have our playback amplifier right here, and the 2 potentiometers labeled swell and sustain, as well as the foot switch, which isn't seeable in this picture, but we see the wire leading to it. That one, right here. Okay, now to the output stage. We have this jack labeled echo in out, and we have the output amplifier right here, and the output lead, which is this wire going outside. Now the last stage, the power stage, is a bit spread out all over the place. You know, that's the stuff with schematics. On paper everything is neatly put next to each other, but in real life, in the actual device, things tend to be a bit different. Let's take a look. So we have the mains wire right here and the mains fuse and the main switch right over here and the motor with the transformer behind it. The first half of the rectification circuit is here. It's 2 big capacitors and a full bridge rectifier. And the second half of rectification is over here. So this is all over the place. Okay, now we have identified every section on the real life picture of the device. And now discuss some interesting facts about each section and components in detail. The 47 kiloohms input resistors are not exactly close to the input terminals as drawn in the upper left of the schematics, but right above the gain potentiometers on the PCB. And they are not to mistake with the resistors on the underside of the input jacks. These pull-down resistors there are missing altogether on the schematics except for input 4. I assume they are a protection against pop noises when the input jack is switched. For the echo in-out socket, pictured right, they spared a resistor and just bridged it to the input force resistor. Let's have a closer look at those input sockets. This is the Echo in-out jack. It's a stereo socket where you can find 3 lugs, tip, ring, sleeve. And it has 2 sides, 3 lugs on each side. When no jack is inserted, the 2 sides are connected via little bridges between the opposite lugs on each side. When a jack is present, the bridge is open and the side closer to us is disconnected from the other side. The inserted jack has contact with the bridges and the signal flows through the farther side of the double-sided switch into the circuit. Now, what is this Echo in-out socket we see here? Basically, it's a send-return breakout for a different way of using the device. Instead of plugging your guitar into input 1 to 4 and plugging the output lead into your guitar amplifier, there were amplifiers around that had a separate Echo send-return jack. You would plug a stereo cable between this jack and the Echo in-out and plug your guitar into the guitar amp. The signal from your guitar would go out of the amp through the tip of the stereo jack and into the Echo in-out socket of the Copycat. From there it would go to input 4 via a short bridge wire, and from there the normal way through the input amplifier and through the recording amplifier onto tape, and from there through the playback amplifier right back to the ring of the Echo in-out and back into the guitar amp. Send return sockets are also found on mixing consoles, and if you had a studio, you could use the Copycat as an outboard delay echo. When the signal goes into Echo in-out, the gain potentiometer of input 4 becomes the master echo send control. The more you crank this up, the more echo you dial into your guitar amp or your console's effects loop. Pictured here, we see the 2 potentiometers labeled swell and sustain, meaning echo volume and echo feedback. A look at the schematics makes it clear. Swell is the green signal path. The echo signal comes from the playback amp and passes the swell potentiometer. Depending on how you dial it in, more of the signal goes on to the output amp on the right side or goes to ground. So the swell pot dials in the amount of echo in the signal mix. That is the mix wet and dry. The sustain pot and the respective signal path are dyed yellow here. Depending on how you dial it in, more or less of the echo signal is fed back into the recording amp, from where it is recorded again onto tape and on and on. So with the sustain pot, you can control the echo repetitions, and ultimately the delay effect becomes a reverb effect, because an artificial room impulse response is created. When engaged, the foot switch bridges the signal path from the playback amplifier to ground, silencing all delay or echo, leaving just the dry signal. By the way, the dry signal is not the original signal that came from your guitar. It always goes through the first amplification stage of the Copycat. Because this stage uses frequency-dependent amplification factors, it already alters, or you might say colors, the signal. We will discuss this a little bit further at the end of this video. Let's have a look at the power stage next. Right here you see the transformer on the left and the motor on the right. The brass wheel on the underside of the motor, or when the faceplate is heads up as it would normally be on the upper side, is a flywheel. You will find this one or the other way in every tape echo. The flywheel is quite massive and its inertia will help to keep the momentum of rotation up. In the best case scenario, slight and short speed variations of the motor are compensated, because when the motor slows down, the flywheel's inertia will keep the speed up for some time. And the other way around, if the motor wants to run faster for short spans, the mass of the flywheel has yet to be sped up. Short spans of speed variation have no detrimental effect that way. The motor itself is a hysteresis motor, or induction motor, a very simple construction of a single-phase AC motor. It seems to be a Japanese make, at least I think these symbols are Japanese. There is M744 stamped on one of the bobbins. Is this the Mitsubishi logo? The label says 4M-30BML. This seems to be the product name of the motor. And it has a timestamp, March 9th, 1979, followed by DA. Hey, the motor is 5 weeks older than me. Now to the oscillator board. The spring that you see on the way is the retention spring for the jockey arm. I did a separate video on that some time ago, so let's move on. A brief recap of what the oscillator is for. In the early days of tape recording, it was discovered that the quality of the recording could be greatly improved when the signal to record was mixed with a high frequency signal. I won't dive deeper into this here, but let me put it this way. The high frequency signal sets the bias for the recording and you cannot hear it. It also does not stay on the tape very long anyway. And secondly, the same high frequency signal is used to erase the tape. In short, this kind of oscillator consists of a capacitor and an inductivity in parallel, so-called resonance circuit, and an amplification circuit, that's a differential amplifier. Therefore, this oscillator is sometimes called a differential amplifier oscillator. It creates a high frequency sine signal, typically somewhere between 50 and 120 kHz. In this case it says 40 kHz on the schematics. In the first red circle you see the wires from the oscillator circuit to the erase head and the recording head. In the second red circle it's the connection from the recording amplifier. So what we have here are the connections marked yellow on the schematics. There is a little trim pot with which the amount of high frequency signal to be mixed with the signal from the recording amp can be regulated. If you feel that the sound recorded on tape is too weak, one possibility is to test bias adjustments by fiddling with this trim pot. The big block in the middle is a pot core inductor. It has two functions in this circuit. Foremost, it is the inductivity for the oscillator. But secondly, it is also a transformer, because it has a primary and a secondary winding. Compare it to the schematics. The primary side has a center tab and you will see those three wires on the right hand side. The two endings of the secondary winding are on the left side. With this step-up transformer, the high frequency signal is transformed up to a much higher voltage. Again, the schematics say 140 volts peak to peak for the erase head and 100 volts peak to peak for the recording head. This may seem pretty much, but you have to keep in mind that the heads are basically electromagnetic coils. The higher the frequency of the signal, the more the impedance of the coil increases. We have a high frequency signal here, and to get the needed amount of current through the coil, the voltage has to be fairly high. In the oscillator circuit you will also find two transistors. They are labeled BFY51 on the schematics, but in my IC300 they are actually PT9790. I don't know why this differs from the schematics, but both are NPN BJTs anyway. Alright, now let's move over to the Super IC. I guess it's okay to rush this a little bit because, as I said before, those units are a little bit like twins, non-identical twins. Some of you might already have spotted the differences on the schematics, but I guess we will find our way around quickly. So let's take a look at this. Alright, we have our input section. And again we have the recording amp and the recording head. And we can easily find the oscillator and the erase head. And there's our playback section. And the output. And again, last but not least, the motor and power section. Time to identify these on the real-life photograph. At first glance, we're easily able to find our way around. We have our 4 input sockets right here and the 4 gain potentiometers, and we see the first IC, the input amplification stage. So, and we can see the recording IC, the recording amplifier right here, again hiding behind that capacitor. But what's this? We have 2 sockets right here that weren't there in the IC300. Well, those 2 sockets are basically the echo in-out and the foot switch. Right here you have the stereo socket, that's the echo breakout socket, and the foot switch socket. As you might have noticed, this aluminum casing was there in the IC300, but it had no real purpose. Well, this Super IC is the earlier model, and in this model the cable compartment wasn't on this side where all the cables went out in the IC300. It was right here. There's a door in the wooden case, and you can basically stuff all your cables in here. And we have also the output lead here and the power cord that goes here and into the mains fuse, and from there to the mains switch and into the motor and rectification. Okay, so let's go on. We see our wires from the playback heads coming in here, but this is a major difference. We see 1, 2, 3, 4 playback head wires come in, and we still have the selector switch right here with 4 switches. So what's the difference between the Super IC and the IC300 is that the Super IC really has 4 playback heads, not 3 as the IC300. But it has no tone switch. There's no tone control switch right here. These are really the playback head selectors. Alright. We know these 2 potentiometers, it's again swell and sustain. And we can identify our oscillator board again right here. So one big difference between these 2 models is that the Super IC had no transformer right here where it was with the IC300, but where is the transformer? Well, the transformer and the motor are one piece in this model. One big difference I forgot to mention, the recording head and the erase head are really one head in this machine. It's a combination head, so you don't see it really, but there's only one cable going to this erase and recording head combo. This is a zoom in on the combination head. You can see the two magnetic head gaps. The input sections look fairly the same, so do 90% of the insides. Different makes and kinds of resistors and capacitors, but nothing too strange. The input sockets are manufactured by Cliff in both units. Here's a detailed view of the playback head selectors. The ICs are a different model though. All four are LM741CN, presumably by Texas Instruments. The swell and sustain pods. So here's the motor that also serves as transformer in this unit. It's from the same Japanese manufacturer, but a different model, 4M-30AML. And of course, it's a few years older, December 18th, 1975, also followed by DA. If you know who the manufacturer is and what DA means, please share it in the comments. The oscillator board looks a bit different. The most notable difference is the lacking of the bias trim pod. There's no such thing in the Super IC. This could become a problem should you ever have to replace the heads for something out of the original specs. Finally, a view of the heads from the backside. You can see the ground wire in the center and the wires to the erase head and recording head right and left. The playback heads, one of them pictured left, have only two wires. Alright. To conclude this video, let's cast a spotlight on those differences that could matter sound-wise. You know, it's a difference if a jack is here or there, or if a fuse is here or there, but as long as it is there, it's really just a design choice. I would like to point out two things that you probably can hear. We have already seen that the two units have different amounts of playback heads. The IC300 has 3 of them, whereas the Super IC has 4. What's the significance? The echo time is made from two factors: the tape speed and the physical distance between the recording head and the playback heads. The sound is recorded onto tape. The tape travels on until it reaches the playback head. This takes a short time span, and thus an echo is created. Different amounts of playback heads and different distances between heads give you different echo options. Let's take a closer look at the amplification stages. We already found out that different types of ICs are used inside the two copycats. But if this means anything sound-wise, and if, what exactly, who can tell? Rather than the OP amp itself, there's other components belonging to the amp stages that definitely have an impact on sound: resistors and capacitors. Differences here we can easily tell by switching between the two schematics. We can see that some values change between the two models, and looking at the playback amplifier, actually a whole lot has changed. There's a whole network of resistors and capacitors here. So what do these changes mean? What's their significance? To assess this, we should first look at a simple example circuit and simulation. What we have here is basically the same as the input stage of the two copycats. We have our 47K input resistor, a gain potentiometer, a coupling capacitor, the first OP amp, respectively the first IC, a resistor and a capacitor above that. This setup is a very basic setup you will literally find everywhere. It is called an inverting OP amp with negative feedback. Why it is called this and what this means, we will discuss soon. At the beginning of the circuit we have a voltage source. This would be the guitar, or in general, the instrument attached to one of the input jacks. I set this voltage source to AC, 200 mV, and a frequency of 440 Hz. At the end of the example circuit I put a voltmeter, well, it's actually rather an oscilloscope. Let's start a simple simulation by activating the voltage source. Mind you, an instrument signal would be much more complex, and it would just cloud our view on what is important here. Much more helpful would be a sine sweep to automatically run a list of different frequencies. But as far as I know, this simulation software here can't do it. But it has the benefit that we can very easily mock up a circuit example. We will change frequencies by hand when necessary. Okay, I called this circuit an inverting OP amp with negative feedback. What does this mean? It is best shown when we visualize the signal in front of the OP amp and the signal right at the output of the OP amp and superimpose those two on each other. As you can see, when the signal in front of the OP amp has reached its upper peak, the signal at the output is at its lower peak. We say that the signal at the output has been phase shifted by 180 degrees, or in other words, has been inverted. Therefore, it's an inverting amplifier. The term negative feedback refers to the fact that a part of the output signal is fed back to the inverting input of the OP amp through a resistor. This resistor has a very specific function in the circuit we're going to look into next. For now, let's remove this capacitor first to simplify it a bit further. We're going to add it again later and see what it does. So, what does the feedback resistor do? In short, its value alters the level of amplification. So when you change the value of this resistor, the volume of the output signal will change also. Let's change values. If we lower the value, the output signal decreases. And if we increase the value, the output signal's level also increases. Of course, only up to a certain point. Let's add this capacitor in parallel to the resistor again. It's called a bypass capacitor, and it functions as a bypass to the feedback resistor. To understand what happens here, we have to remember that a capacitor also has a resistance. It has an infinite resistance for DC. That means DC cannot pass the capacitor. But it has also a resistance for AC, or as it is called, a capacitive reactance. What this basically means is that the resistance of the capacitor is different for different frequencies. Some frequencies pass easier than others. As a very general rule of thumb, you remember that the lower the value of the capacitor is, the higher the frequencies can pass it. This is a very general rule of thumb that needs an example to make it more clear. For example, the coupling capacitor at the input has a value of 1 microfarad. This is such a high value that basically all frequencies can pass it without resistance. This capacitor is just a resistor for DC, to stop DC bleed into the amp circuit. If we lower the value of this capacitor more and more, it will start to inhibit the lower frequencies, 1 Hz, 10 Hz, 100 Hz, but it will let everything above that pass. So we have established that the bypass capacitor will be a resistor for certain frequencies, and it will let other frequencies pass without resistance. We learned earlier that the increasing of the feedback resistor leads to an increase in output volume, and a decrease of the resistor leads to a decrease in output volume. If that capacitor lets some frequencies bypass the resistor, those frequencies will not be amplified. So by changing the value of the capacitor in the circuit, you can basically decrease the volume of all frequencies from a certain point on upwards. Let's play with the frequencies a little and see how the overall volume at the amp's output changes. At last we can also change the capacitor values a little. It would need further analysis, but what I said earlier, that the input stage already alters or colors your guitar's tri-signal, seems to be not entirely true, but also not entirely wrong. The capacitor value of 100 picofarad seems to only filter out high frequencies way above 22 kHz. I suspect that this is more to filter out high frequency bleed that the input jacks might collect. It's a frequency region that is still in the hearable spectrum if you have good ears left, but I don't think that this cutoff contributes a lot to your guitar's tone. What might be of much more hearable effect is that the input impedance of the first amp stage is defined by this 47K resistor and the potentiometer. If you crank the gain up, it might be around 50K overall. This is much lower than the 1 megohms that guitar amps have as input impedance normally, and this will probably steal some highs from your guitar signal. So even by that, the copycat has a hearable effect. As I said before, more can only be determined by much more analysis. For this video, let's cut it right at this point. Thanks for watching, see you next time.